Good afternoon, depending where you are in from. Today's class will be looking into several things or units. We are marking the beginning of the new class today, and I try to send messages across via mail so that you get the notification and join the class. My name is Dr. Anayo Chukwu, popularly called Analyst. I'll be your facilitator for this class or for this course. So that is cit344, Introduction to Computer Design. That is the title. I want to emphasize or re-emphasize the procedure to go. In the e-learning platform, I've uploaded the material for the week. I've also dropped some areas or topics for discussion for the week. Do all you can to participate in the discussion forum where you have to relate with other candidates or students for this course. You should try to attempt the discussion or participate in the discussion forum where you contribute your own quota to the pertinent questions dropped. At the end, you'll be assessed. Every week, we'll be meeting once in a week. That is Thursday by 3 p.m. If there will be a need for us to change the time, we all will be communicated. So in a jiffy, we will start for today's class, and the areas we'll be looking at is we'll look at module 1, module 2, probably module 3, as case our time will permit us. Module 1 we'll be looking into is the introduction to numbers and codes. And under this, we'll look at different units like types of number system 1, types of number system 2, under unsigned and signed binary numbers, and lastly, codes. We'll look into it. Moving forward or moving on, we'll look at types of number system 1. I want to let you understand that number system is a fundamental approach through which every computing is made. I repeat, a number system is a fundamental that have been acclimatized in every aspect of computing. Computer system is made up of numbers. I could remember during my year 1 in the university. We were studying, then it was GS 102, philosophy and logic. One day, an argument arose on how man began, or what in other words called the origin of man. Our lecturer was trying to justify or to lay emphasis or support on the view or opinion that man is made up of numbers or originated from numbers. Likewise, other philosophers say that man is originated from apes. You know about the law of Charles Darwin, how man, the Homo sapiens, Homo erectus, and the rest of them. So, the man tried to inculcate or support the motion that says man is originated from numbers. Well, if you listen to his arguments properly, you discover that you may somewhat shift to support his own view that man is made up of numbers. The angle is coming from that everything you do in this life is all about number. It will be difficult to mention anything without using number. It must be originated from numbers. So computer is all about number. I'm taking time to explain to you what this topic is emphasizing on, because time will not permit us to begin to read line by line. I want to explain this thing to you so that by the time you have of course, the material have been shared in the platform through e-learning, you can access it. Make our time to read it and then make note from it. I'm here to break the barrier, the ambiguity, the ambiguous that leads to hard understanding of this topic. By the time you understand it in real life scenarios, in a general perspective of lives, by that, you'll be able to link it and understand what you intend to achieve here. So remember, in what we call machine learning or assembled language, we discussed about computer language. We said that computer language is all about ones and zeros. That is computer language, or what we call machine language, ones and zeros. As I speak, as you communicate through voice, through audio, through video, through text, there is an assembly language that is very busy converting the high-level language to a low-level language. And that low-level language is called computer language, which is zeros and ones. So you have a glimpse understanding of what we need to achieve in this lecture. It's all about reading it. It's all about knowing the intent, knowing what the topic is talking about. This is why it is very important that you need to understand it very, very well. So we'll continue to discuss what we intend to achieve in this area. Thank you. Now, what is the intended learning outcomes? At the end of this unit, you'll be expected to know what is called decimal number system, how to manipulate fractions of decimal numbers, understand what binary numbers is or mean, and how to manipulate binary arithmetic. You also expected to know how to convert binary to decimal, and lastly, convert decimal to binary. It's very, very important because during secondary school level, even the junior class, we talked about binary numbers. We talked about decimal numbers. So it's worth of you reconnecting yourself with those days we discussed them in mathematics. Okay. So now, what is decimal number systems? It is expresses as a base of 10, meaning that it has 10 allowable digits ranging from 0 to 9. Then in that scenario, those digits are arranged as follows. Maybe 0, 1, 2, 3 to 9. Using these digits, single digits, then different values can be emerged or be represented. So every number above digit 9 is gotten from a systematically combining two or more values. Take for instance, 10 is represented by a combination of 1 and 0 value or digits, resulting to number 1, 0, 1, 0. 1 is a single digit. 0 is also a single digit. When you combine 1 and 2, the two of them form 2 digits. And this is 1, this is 0. So it becomes 1, 0. If you add the two of them, it becomes 10. So moving on in that direction, we'll be able to explore when that digit is extinct 2 and the digit become 3 combined together. Or for instance, when it moves to what 3 digits, it becomes hundreds, 100, 200. I say this is 1, 0, 0, become 100. This is 1, 0, 0, 0, become 1000 in that dimensions. For example, we have 275, where 2 is less than 7. However, 275 represents 200, whereas 7 represents 70, and the left out the digit has the highest weight, in the rightmost digit has the lowest weight. Therefore, 275 can be written in form of expression in terms of the base, like we see here. 2 times 102 plus 7 times 101 plus 5 times 100 equals to 200, plus 70 plus 5, all will amount to 275. So in the same directions, we want to see 10 that will represent the base of, let's say, 102, 101, 100, represent a weight of 110 and 1 of the numbers 2, 7, and what? 5. Okay, so moving on in these dimensions, we can say that the general equations from any number system is given as a base 5, a base 4, down to a base 0. Once it shifts from 0, it now go to left hand side, it now become minus a base 1 minus 1, a base 1, sorry, a base minus 2, a base minus 3 in that dimensions, depending if you are going to the left. If you are going to the right, it becomes positive. If you are going to the left, it becomes what? Negative. So this is how we were able to say that the R there is the base and the AI there must be less than R, which is the base. Likewise, you see fractions in the decimal numbers. So where you can see one that is, maybe you want to divide 3 by 10. You say 3 divided by 10, you say 9 remainder 1. You see it? So that remainder, that is become a fraction. Dot 1.5 means 1 remainder 5 in that dimensions. So moving on here, we have binary number system. Binary number system. Remember that in binary number system, we refer it as 2. One is binary. Binary means 2. 2, binary. And the binary digit is 0 or 1. Is known as bits. Below is a number, below is a decimal equivalent of the binary number system. We can then have decimal number, binary number, decimal number, binary number. In zeros, let's say 1 to 9, this is decimal number, which is in binary number, you have 0. Because 0 divided by 0 is 0. Then here 1. 1 divided by 1 is 1. Here is 0. 1 divided by if we divide this one, you see, is represented in these dimensions. So 2 divided by 2 is 1, remainder 0. So 2 divided by 3 is 1, remainder 1. That is where it is what appeared. Okay. So like this 4 now, we are talking about 2 binary. 2 divided by 2. 2 divided by 4 is 2. 2 remainder 0. You write down 0. Then 2 divided by 2 is 1 remainder 0. That is why if you divide 2 by 4 in binary, you have 1 0 0. And then the same way, like if you divide 2 by 5, 2 divided by 5, you have 2 remainder 1. You write down the 1. You now divide 2 by 2. Is 0, remainder 1. Mean is 1, remainder 0. So that is how you divide, use to divide this to get this. Likewise, when you use 2, apply 2 in 10, and then you also achieve the binary numbers. All right. So by the time you look at the brief right up here, you see that Counting a binary number system is similar to counting a decimal number system. In a decimal number system, a value larger than 9 has to be represented by 2, 3, 4 or more digits. Similarly, in the binary number system, a binary number larger than 1 has to be represented by 2, 3, 4 or more binary digits. So when you read further, you get to see how it works. So the same way it happens in fractions in binary number system. I believe you are. If you have any question, please feel free to ask or just raise your hand. I will let you know or get in touch with you. If your network cannot allow you to ask the question or raise your hand, you can drop your message or questions in the chat box. Okay, and by the end of the discussion, probably I will upload it on YouTube, where you can also have at your scheduled time, you can listen to the lecture. And while doing that, if you're the first time, make sure that you subscribe to the channel so that you keep getting updates of other upcoming lectures. Like you see, binary additions. Binary additions in identical to decimal additions by adding two binary bits. Some bits and a carry bit are generated. So you can see fine number, second fine number, sum and carry. You see, so by the time you look into it, the question by they say the first three addition give a result 0, 1 and 1 respectively, which can be represented by a single binary digit. The fourth addition result in the number 2, which can be represented in the binary as 102. So if you want to perform this subtraction, is also there. Based on my explanation before, you see it is very easy now to walk through. Binary divisions. Division in binary follows the same procedure as a division of decimal numbers. For example, looking at figure 1, the division of binary numbers are as follows. So you can see it from the figure 1, binary division. So let me just look into sometime like some of the weight methods. Binary bits having a value 0 do not contribute any value towards the final sum expression. For instance, the binary number 10110 base 2 is therefore written in the form of an expression having weight 2 raised power 0, 2 raised power 1, because if you count it, it has 1, 2, 3, 4, 5. We have 5 values. The first one now is start from 0, 0, 1, 2, 3, 4. That is 2 raised power 0, 2 raised power 1, 2 raised power 2, 2 raised power 3, and 2 raised power 4. What we are trying to say that anything raised power 0 is 0. Anything raised power 0 is 0. Take for instance now, the bit 0, 1, 1, 0, and 1 respectively, with 2 raised power 0 and 2 raised power 3 do not contribute in the final sum, as the binary bit corresponding to its weight have the value 0. Take for instance, 1 times 2 raised power 4 plus 0 times 2 raised power 3 plus 1 times 2 raised power 2 plus 1 times 2 raised power 1 plus 0 times 2 raised power 0. in this dimension now, they started from the least, the last to the highest to the lowest. Nevertheless, even if you start from the lowest to the highest, you will still achieve the same result. Take for instance here, 2 raised to power 0 is what? 0. Is it like 0 times 2 raised to power 0 is still 0. Then the next one is 1. The first value. This is 1 times 2 raised to power 1 is 2. So by the time you add it up here, you remember that when you say 2 raised to power 1 is 2, 2 raised to power 2 means 2 times 2. 2 raised to power 3 means 2 times 2 times 2, which is 2 times 2, 4. 4 times 2 is 6. Then 2 raised to power 4 is 2 times 2 into 4, which is 2 times 2, 4. 4 times 2, 8. 8 times 2, which is what? 16. So you see where 2 times 2 times 2 into 4 will give you 16. And then whatever thing that is multiplied by 0 is 0. That is what you see 0 here. And 2 raised to power 2 is 4. 4 times 1 is what? What do you have is what? 4. Then 2 raised to power 1 is 1. I mean, it's 2. 2 times 1 is 2. Anything multiplied by 0 is what? 0. By the time you add 16 plus 0 is 16, plus 4 is 20, plus 2 is 22, plus 0 is still what? 22. And that's why you had the value of what? 22. So apply this in other calculations as case may be. So the same thing that happens when you don't want to do, once you want to convert decimal to binary. So at the end of it, you should be expected to demonstrate with a good example the different methods of converting binary numbers to decimal numbers. Therefore, in conclusion, the decimal number system has 10 unique digits: 0, 1, 2, 2, 9. Using this single digit, 10 different values can be represented. 10 different values can be what? Represented. Values greater than 10 can be represented by using the same digits in different combinations. Binary indicates a base 2 number system having only 2 numbers, 0 and 1. The binary digit 0 or 1 is known as bits, as we discussed earlier. All right, you have, or you can go through it. Then finally, we have other areas or works you can visit to get deep understanding on the topic. Nevertheless, as I stated earlier, if you have questions, feel free to drop your message or questions in the chat box, or even in my YouTube channel. You can drop your message. I will answer or attend to it. Thank you. So moving on to Unit 2, types of number system 2. Here we'll look at hexadecimal numbers when you are counting from 8-digit value. Counting in hexadecimal number system, binary to hexadecimal conversions, hexadecimal to binary conversions, decimal to hexadecimal conversions, and then the other way around, also hexadecimal additions and subtractions. I know some of these you must have come across it during your year 1, where you talk about number system. It's all about introduction to computer system. You discuss them here. So we want to see how this can be cumulatively utilized for computer design. I know it's quite long. Some of us have dropped or work with mathematical related problems. Some of the things we are discussing will be sounding like a foul language, to be sounding like a rhetorics. But I believe it that by the time you go back, begin to go through it, read it, add to my explanation, you understand what you expected to do, because my interest is for you to have this course A, to pass very well, do your TMA and get your score. But it will be difficult when you don't learn to practice. So we also look at the second part of this discussion. We look at octa number systems, not 10 digits counts. Counting in octa, octa is 10, hexa is 8, nano is 9, pentagon is 5, just in that dimensions. Just like we say binary is 2. So binary to octa conversion, octa to binary conversion, decimal to octa conversion, octa to decimal in that dimension, to octa to addition and subtraction. So we'll look at all of them, and then we'll be able to, at the end, try to explain what hexadecimal numbers, binary to hexadecimal numbers, decimal to hexadecimal, how to convert from hexadecimal to octa, octa to binary. That is the take home in this unit. So moving on, representing hexadecimal numbers. What is hexadecimal numbers? We represent even small number, such as this is 6918, requires a long binary string. If you use 2 to divide 6, and if you use 2 to divide 9, if you use 2 to divide 1, if you use 2 to divide 8, at the end, combine them to 0s and 1. This is a long digit you are going to get. So the hexadecimal number system is a base 16 number system, and therefore has 16 digits, and is used primarily to represent binary strings in a compact manner. Take, for instance, in table 1, each hexadecimal numbers digit can represent a 4-bit binary numbers. The binary numbers and the hexadecimal equivalents are listed as we see in table 1. Decimal 0 to 9, 7 rather. This is a binary in 4 digits, or in 4 bits, 4 digits, 4-bit binary. This is 4. This is hexadecimal. This is a decimal, starting from 8 to 15. And then likewise too, we see them and they see how it is. Sometimes 1 is 10. We use A alphabet to represent 10 digits. When is 11, we use B to represent 11 digits. We use C to represent 12 digits. We use D to represent 13 digits. We use E to represent 14 digits. And again, F to represent 15 digits. So by the time you do the counting, this is exactly what you are going to achieve from hexadecimal, which is base of 16, as it is in table 2. Okay? So you can see the conversion here in 4 digits. Break each of them and break them into 4. So into 4, you now check the arrangement of the values, then you now represent the value. Replace each group by its hexadecimal equivalent. So if you check, this one is 11, like let's say 1101. Let me see. Let's go to table 1. 1101. 1101, which is D. 1101 is D, which is 13. And that is how you see D here. Just break this thing into 4 decimal, 4 bits. Like this one, after that one, the next bit is next 4 bit is 0110. Let's check table 1, 0110. 0110. You see, 0110 is what? 6. And that's why you have 6 here. Then the next one, maybe let me just highlight this. Maybe say yellow. Then probably I will highlight the next one with maybe say green. I'm picking them in 4 bits. In 4 bits. Let me highlight it with another color, say blue. Then another bit. So pink. Then the next one to red. You see it as I highlighted it now. You see, you now begin to trace the bit by bit. Then in dividing it into 4-bit group, you see the first one is a D, which is 13. This one is 6. Then the next one is B, which is 12. If you divide 12 by 2 in binary, you achieve 12, which is B. The next one is 9. Then next one is 6 as well. So by the time you add it, you achieve that which you are expected to achieve. Thus, all this is represent what? In hexadecimal is D6B96. Just add this value. In case you are in the exam, you asked to convert a certain value to hexadecimal. Do you get it? So you should be able to achieve that. Likewise, when the values like that, then if you want to convert it to hexadecimal, all you need to do is just break them into 4 binary. Well, binary is 2. That means you pick it to 2 digits in that dimension and then achieve your result. Just read the instruction very well. Very simple. So all these things are what we just discussed. By the time you read it, whether it's in base, whether it's in base, just read it and then you see how it is being converted. Note this, value of 10 is A. Always, always know this very value. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. Always note that very well. In the exam, it will always come out. Very, very important. So with that, if other calculations you want to do, it's very, very easy. Just read it and understand how it works. Okay. And if you want to add, use the same or read, understand the conditions, the instructions for you to the rules of addition and subtraction that are used to add and subtract numbers in decimal or binary number system apply to hexadecimal addition and subtractions. Hexadecimal additions and subtraction allows large binary numbers to be quickly added and subtracted, as we can see from this. So if you understand about hexadecimal, the same thing applies in octal number systems. In octal number systems, because it provides a convenient way to represent the long string of binary numbers. The octal number is based on 8 number system with digits ranging from 0 to 7. Understand this. Hexadecimal is 16 base number. And in octal numbers is based on 8 number system. It appear like octa is opposite of hexadecimal octal numbers. Hexadecimal is base 16. Octadecimal or octal numbers is base 8. So that is the way it actually worked. So as you can see, octadecimal numbers 0 to, let's say, to 9 or to 7. This is the binary of this value of decimals. Then octals, this one is 0, this one is 1. And they're now picking the figures attached. It's more of like decimal places. Just move on, you understand the concept better. So let's look at binary to octal conversion. Converting binary to octal is a very simple. The binary string is divided into small groups of 3 bits. Starting from the least significant bit, each 3-bit binary group is replaced by its octal equivalent. Remember one thing, hexadecimal is counted by 4 bits. Then in binary to octal or octal conversion, you group by 3 bits. Then at the end, you now find the value. If you pick any, you just break them into 3 bits, as you can see. Pick it 3 by 3, then you assign the value based on the table 4 and table 5. Combine it, very simple. I think with that idea, you can use it to perform the remaining. You can now add and subtract. Okay. So in conclusion, in this unit, we talked about hexadecimal and octal number system, counting in hexadecimal and octal, hexadecimal and octal arithmetic, conversion of hexadecimal to binary in that dimensions. So that we come to the end of unit 2. So moving on, we'll also look at the next units, which talked about unsigned and signed binary values. Unsigned and signed binary numbers. Here you should be able to know the concept of signed and unsigned number representations and how to complement the techniques therein. So we'll move on. We have looked at the decimal number systems and the binary number systems in the previous units. But we'll now look at how important to understand how each of the number system we discussed earlier works. An assigned number or binary numbers has no arithmetic sign and is always positive. Take for example, unassigned decimal numbers are the numbers on your mobile phone keypad. Okay? If you pick your phone, even in your keyboard, laptop keyboard, those numbers there is assigned what? So they all are unassigned decimal numbers. Likewise with your phone, your age, and many more one can think of without sign. Also, an 8-bit unassigned binary integers are number represented from 00 base 16 from F, which is F16 in that dimensions. What are we discussing here? Let's look at the magnitude. That some of the numbers you see, any of the number, whether letter or alphabet, is automatically a positive sign. If you don't say, maybe say +1, +2. No, any number that stands on its own, whether 0 or 1 or 2, is a positive numbers until you assign minus value into it. For instance, now, +2 base 10 minus 10 minus 0. The magnitude here is we have 0, 1, 0. So the sign value here is 0. So the same way it happens in the other way around. By the time you look at the next table, you see it. You see this one positive sign, this one the magnitude is negative sign. All right. So by the time you actually look into it, you discover that the values there, like for example, 9's complement of the following numbers: 13, 33, 5, 6, 12. We have 9 complement 9 plus 13. If add 13, you just invariably look into it. 9 minus 3 is 6. 9 minus 1 is become 8, 6. Here, 9 minus 3, instead of, 6, 9 minus 3, again, you also have 6. So the same way we have here, I will talk about complement. The 9 complement of a decimal number is obtained by subtracting each digit of the numbers from 9, as in table 2 shows us. Say it. Complement, subtract that number by 9, you will get the same value. Okay? And that is what they perform there. If you go through, you see the values there. So you just look into it. We have one complement, addition, one complement. You see some of subtractions, one complement subtractions, and 2 complements additions, and 2 complement subtractions, 2 complement additions, and in that direction. Just take time to look through it. By the time you are done, what is the essence of this? Binary numbers could be assigned or unassigned numbers, where 0 is used to represent positive binary numbers and 1 is used to represent negative binary number. In a conventional manner of these signed numbers or binary number, for signed binary numbers, the MSB, that is most significant bits, number 0 or 1, represent the sign of the binary numbers. However, On unassigned numbers, all bits of the numbers are used to represent the number. All bits of the number are used to represent the number. So by the time you look into it, even the complement techniques are mostly ones and twos complement, were initiated in order to enable computer understand and operate arithmetic operations the same way humans understand it, thus giving us as output the expected result. Most modern computers are designed with twos complement to effectively carry out its arithmetic operations. So at the end of the whole thing, you should be able to understand what is the concept of unassigned and signed numbers. Understand the complement techniques, both the one complement and the two complements. So finally, for today's discussion is codes. The codes. These are some of the standards way of coding a computer system. I could remember when we were having some training with military personnel. Anytime we are in the jungle or we're in the field, they use a code language to communicate with one another. In the military, they have their own specific code language. Likewise to other conventional society. Sometimes you may be passing, somebody will tell you, Ahua. It's only those who are in the military understand what it means, Ahua. Sometimes you hear esprit de corps. Only someone who have served in military or paramilitary will understand what it means by esprit de corps. I get it mean. The same way those who are in a other society, in other words, what they call Ogboni society, Orcot, and the rest of them, they have their own code language or sign. Those who are in the court or courtism operations, they also have their own unique code of communication. Okay? The same way in some ethnicity, they have their own code language, especially in a diverse cultural way. I remember a certain clan that have their members spread across the society. And they always have one central language or code. This is to unify their language style, that they are from one, irrespective of where you are living. They have one ancestral home. What am I saying? One clan, they call it Eza Nation or Eza clan, is located in Ebonyi State, southeast geopolitical zone in Nigeria. They will say Eza Jikotaron, Undulan, Olulan. I asked, what does that mean? Eza Jikotaron. You are expected to echo Undulan, Olulan. This is to unify that they are one with one language. Here, we want to relate all the discussion now back to computer system. So you're welcome back to computer design, how those codes helps computer to be unifiedly designed. So that is why we now have all these codes. We have SS code, BCD code, gray code, alphanumeric code, ASCII code, and extended ASCII code. Okay, so we'll look them into one after the other. Say a code is a computer palace. Is a generic term for program instructions used in two general senses. The first sense refers to the human readable source code, which include instructions written by a programmer or developer in using a computer programming language. The second refers to the executable machine code, which includes instructions of program that were converted from source code to instruction that computer can understand. Okay, so we look them, they consider the decimal number range from +7 to -8. These positive and negative decimal numbers can be represented by two twos complement, and the magnitude of these positive and negative numbers cannot be easily compared, as the positive and negative numbers represents in two complements form are not represented or uniformly increased scales. So we look into it from the table. Two complements, SS8 decimal, two complement SS what 8. So you go through it based on my explanation. You see we have BCD, binary coded decimal. They use the same operation to discuss them, as you can see in table 2. So yeah, same way, if add this, operational adding, you see 1 + 1 is 2. 1 is 2 minus 2, it becomes 0. Carry 1. 1 + 1 is 2. 2 minus 2 is 0, it becomes 0. Carry 1. 1 + 1 is 2. 2 minus 2 is 0. Carry 1. Then 1 + 0 is 0. 0 + 1 is 1. That is why you have this in additions. Then here now, 0 + 0 is 0. 1 + 0 is 1. Then 0 + 1 is 1. 0 + 0 is 0. Here, 3 + 5 is 8. And 2 + 4 is 8. See how the addition works. It has rules. Just understand the rules. Chicken eye. Badamwa. Once you understand the rules, apply that rules. Badamwa. Kusi wahala no dey. So the same way we will talk about grayscale when I apply the same way, and it also works. Then we also look at alphanumeric, both alphabet and numbers, integrate them together to work. For instance, when you say 1, 2 to 0 to 9 binary, we have 10 is represented as what? A, 11 as B, 12 as C, 13 as D, 14 as E, 15 as F. You see it. When you combine them, maybe say A1 or 0 or 2B, you are now interwoven with the letters. Okay? So that is what it means. Then ASCII, American Standard Code for Information Interchange. This is uniquely adopted. In every exam, it always come out. Uniquely adopted to maintain the standard. Everything you are producing have a standard, and this uniquely adopt this standard to enable you to do what? Achieve it. So the standard is being maintained and then is being adhered to. Okay. All these standards is just like ASU standard. It's also used in their own way, but this one for computer way, it uses ASCII to ensure that we have maintain uniformity for data exchange. It means if you send something from Nigeria, somebody in America will receive it because they understand the rules. If you send something in America, somebody in Europe will still receive it. If you sell something in Nigeria, somebody in the Middle East, maybe if you are sending to Israel or Lebanon, the person will still receive it because it maintains a generalized standard code for exchange. This is what it's all discussing about. I think that has bring us to the end of today's discussion. So in all of it, SS8 is obtained by adding number to the lowest number 8 in the range such that the result is 0. Whereas binary coded decimal BCD code is used to represent decimal digits in a binary. What does it mean? BCD code is a 4-bit binary code. The first 10 combinations represent the decimal digit 0 to 9, as earlier explained. Then the gray code does not have any weight assigned to its bit position, but it is not a positional code where different or that is different from the unassigned binary code, as successive values of gray code differ by only 1 bit. Finally, the ASCII code that is or stands as American Standard Code for Information Interchange is a 7-bit code representing 128 unique codes, which represent the alphabet characters A, B, C to Z in a lower case and upper case. It could be small letter or could be in capital letter. The decimal number is 0 to 9. Punctuation marks and control characters are associated with ASCII code. So finally, at the end, you should be able to understand the various codes such as BCD, binary coded decimal, gray codes, ASCII codes, alphanumeric codes, SS codes, and their general characteristics. Thank you once. As I stated earlier, even if you miss this class, make out time to listen to the recorded video or class. I will upload it and share the link so that you try to go through it. Above all, make sure you subscribe to the channel for more updates. If you have any question, drop in the channel comment section or in your group discussion or group forum discussion or discussion forum in your platform. Thank you. See you next week, Thursday by 3 p.m. Thank you.